Welcome back to the Transformer series. In the last video, we solved the input problem. We learned how raw text become token IDs, then dense vector through the embedding matrix. So now, each word has a rich numerical representation that captures its meaning. But there is a problem, a really fundamental problem that we have not addressed yet. Those token embedding carrying meaning, right? But they carry no information about position. So the token knows the meaning but do not know the position. Self-attention compares every token to every other token in parallel. There is no sequential processing. No first, then second, then third. It treats the input as a bag of tokens. A set with no order, right? But word order is essential to meaning. Without it, the dog bit the man and the man bit the dog are the same thing to the model. Both sentences have the exact same words and the exact same embeddings. The only difference is the order, and the transformer has no way to see it. We need to fix it. Here's what we will cover. First, why self-attention is naturally order blind and how the original transformer fixes it. Second, the sinusoidal position encoding formula and what those different frequencies actually means. Third, why sinusoidal encoding can generalize to longer sequence. And fourth, why the field evolved from absolute position towards relative method like RoPE. So let us really feel this problem before we fix it. Self-attention compute relevance score between all pairs of tokens. But nothing in those computation knows which token come first. Look at these two statements. The dog bit the man and the man bit the dog. Same word, same set, without position information. Self-attention produce identical score for both. It literally cannot tell them apart. And you can try it yourself. Let's shuffle them. Right? Watch the tokens rearrange into random orders. And the key point is that the attention mechanism would not notice. Same token, same dot product, same score. That is the problem. And here is the mental model that makes this stick. Imagine you have a fridge magnet with words on them. The magnet themselves carry meaning. Dog means dog, man means man. But the sentence meaning depend entirely on the order you arrange them on the fridge. Without the order, you just have pile of meaningful magnets with no sentence. Position encoding is like putting a small address label on each magnet. Position 0, position 1, position 2, so on and so forth. The solution is beautifully simple though. Before the token embedding enters the transformer, we add a position vector to each one. The equation is just addition, right? Take the token embedding, that is the vector saying what this word means. Take the position encoding, that is the vector saying where this word sits. Add them together and the result is a single vector that carries both piece of information. What the token is and where it is in the sequence. On the screen you can see this visually. The top row shows the token embedding for each word. The middle row shows the position encoding, pos 0, pos 1, pos 2, and so on. And then together you get them in the bottom row. Each token now carries both its identity and its address. The is at 0, cat is at 1, sat is at 2, etc. etc. Now you might wonder, why simple addition? Because it is the simplest way to combine two sources of information into one vector. The model can learn to disentangle the what from the where as needed, right? And there were two approaches to creating this position vector. One is sinusoidal, fixed deterministic vector computed from mathematical formula with no extra parameters, and the ability to extend to length beyond training. And another next one is the learned. The model learns to look up table of position vector just like it learns token embedding. The original paper that introduced transformer found both give nearly identical result. We will start with sinusoidal because it is the one the paper used, and the math is surprisingly elegant. The original transformer used sine and cosine, right? Basically sine and cosine waves, and that too at different frequencies to give each position a unique fingerprint. Here is the equation, and I know they look dense, so let me translate them into plain language. For each position in the sequence, you generate a vector. Okay, you fill the even number slot with sine values, right? Even number slots with sine value, and odd number slots with cosine values. And here is the key trick. Each pair of slot use different frequency. Okay. The first pair oscillates very fast. It changes rapidly from one position to the next. The last pair oscillates very slow. It barely changes over hundreds of positions. The number here, that is 10,000 in the denominator, is just a scaling constant that controls how these frequencies are spread out from fast to slow. Here is an analogy that makes this click. Imagine a clock with dozens of hands, I'm saying, right? Each spinning at a different speed. The second hand spins fast, that is high frequency. The hour hand spins slow, that is low frequency. At any given moment, the combination of all hand position is unique. No two moments in time have the exact same configuration of all hands. That is exactly how sinusoidal positional encoding works. Each dimension is a hand spinning at its own speed, and each position gets a unique combination. The power of sinusoidal encoding comes from mixing fast and slow waves. Each captures a different scales of positional information. On screen, you can see 3 waves. We can use the slider to change how many dimensions you are looking at. The top wave oscillates fast. They wiggle up and down with very few positions. The bottom waves oscillates slowly. They barely move, right, across the entire sequence. And this is not just a visual trick, it is the core design insight. Fast move, fast waves in early dimensions are excellent at telling apart nearby position. They can distinguish position 5 from position 6 because the value changes a lot between adjacent position, but they repeat quickly, so they cannot tell apart the position that are far apart, right? Slow waves in the later dimensions are ideal for capturing large scale positions. It is the token near the beginning or the end of the sequence. The slow waves can answer that. The slow waves can answer that, but they cannot distinguish two adjacent positions. The slow wave can tell whether it's a start or an end, but they cannot tell whether it's a fifth or a sixth position. And we can increase the dimensions also, so this becomes like a fingerprint. And that is why you need both. By combining fast and slow waves, each position gets a unique multi-frequency, right? The fast wave handles fine-grained distinction. The slow waves handle coarse position. Together, no two positions share the same encoding vector. When we compute positional encoding for every position across every dimension, we get a distinctive pattern that you can visualize as a heat map. On the screen, there is a heat map. Each row is one position in the sequence. Each column is one dimension of the encoding. Right? Each row is a position and each column is a dimension. Red means positive value, blue means negative value. We can use the slider to change how many positions and dimensions you want to see. This is what makes sinusoidal encoding work. It gives every position a unique signature that is different from every other position, using nothing but a mathematical formula with zero learned parameters. One of the most useful properties of sinusoidal encoding is their ability to extend beyond what the model saw during training. Sine and cosine have a special mathematical property. For any fixed offset, the encoding at one position can be expressed as a linear transformation of the encoding at another position. In plain terms, this means the model can learn patterns like 3 positions ahead or 5 positions behind as a consistent operation. The relationship between position 10 and 13 looks the same as between position 200 and 203. The relative offset is what matters, not the absolute number. And this is where sinusoidal has an advantage over learned embedding. Learned embedding are fixed size lookup tables. If you train with sequence up to length 512, let's suppose position 513 has no embedding. The model has literally never seen it. Sinusoidal encoding are computed from a formula. You can compute the encoding for position 513,000 or 10,000. The math works the same. The signal exists for any position. Now, I do want to be honest here. In practice, simply computing sinusoidal encoding for longer position does not guarantee the model performance or perform well. The attention pattern learned during training may not transfer perfectly. But compared to learned embedding, which have a hard cutoff, sinusoidal encoding at least provide a signal. This is graceful extension. This graceful extension was one of the original motivation of the design. The original paper tested both approaches. and reported their finding directly. On the screen, you can see the two approaches side by side. Sinusoidal, zero extra parameters are needed, can compute for any position, has linear shift property and requires no training. Learned embedding is one vector per position, hard cutoff at maximum trained length. No built-in shift property, but learned end-to-end with the model. And here is the key finding from the paper. In their table, replacing sinusoidal encoding with learned positional embedding produced nearly sort of identical result on translation benchmarks. The model performed equally well either way. The paper chose sinusoidal for the main model partly because it requires no extra parameters and offer the theoretical generalization advantage. But in practice, many later models, including BERT and GPT-2, chose learned position embedding anyway. The fixed maximum length was acceptable for their use case, and learned embedding can adapt to the data distribution. So, the choice between fixed and learned became less of a debate and more of a engineering preference. Now both sinusoidal and learned encoding share a fundamental property. They assign each position an absolute address. And that turns out to be a limitation. Absolute encoding says this token is at position 128, but many language tasks care more about relative distance. This word is 2 positions away from that word. Think about a phrase big red car. The relationship between big and car is always 2 positions away in the same direction. It does not matter whether this phrase appears at the start of a short sentence or in the middle of 2000 token document. The relative distance is the same, and that is what the model should care about. But this absolute encoding, position 5 and position 500 have completely different encodings even when the local pattern is identical. And once context length grew and transformer were applied to more diverse tasks, it became clear that I am at position 500 is often less meaningful than I am 5 tokens away from the thing I need to attend to. This realization launched an entire subfield of research into relative position encoding. The next evolution of integrated distance information directly into the attention mechanism rather than adding it to the embedding at the input, right? That was the next evolution, sort of directly integrate the distance information into the attention mechanism. Here is the contrast. In the absolute approach, position info is added once at the input before any attention computation, right? The attention mechanism itself has no awareness of distance. It must learn to extract positional information from the combined embedding. In the relative approach, the distance information is injected directly inside the attention computation. When the model computes how should position 10 attain to position 7, it can now explicitly factor in they are 3 positions apart. And this distance term is the same regardless of where in the sequence those positions are. In the original attention equation, the score between 2 positions depend only on the content at those positions. Relative position method add a distance dependent term to the attention score. This is the direct modification of the core attention maths. Position is no longer something that model has to extract from the input. It is given as an explicit signal during computation. And this made a real difference. Relative encoding made transformer better at generalizing across different sequence length. They informed they informed performance on tasks where local patterns matter regardless of absolute position, like parsing syntax, processing long documents, handling variable length input. The most popular modern approach is rotary position embedding, which bakes position into attention in a mathematically elegant way. Here is the core idea. Instead of adding a position vector to the token embedding, a rotary position embedding rotates the query and key vector as a function of their position. Right? On screen, you can see the animation. Blue arrow is a query at position 5. A red arrow is a key at position 8. Both are rotating at the same speed, and the angle between them stays constant at 3, which is relative distance. When you compute the dot product of these two rotated vectors, the result depends only on the relative angle, not on the absolute position. If we shift both position by 100, the individual arrow points somewhere completely different, but the angle between them is 3. And that is elegant, right? That is the elegant part. So the model encodes absolute position through rotation, but the attention score naturally depend on relative distance. You get both properties from one mechanism. We are not going to dive into the fully rotation maths today, but the takeaway is clear. Model become dominant positional encoding in the modern large language models. This particular model, because it naturally captures relative position, has a good extrapolation properties, and add a minimal overhead. Position information can be injected before attention, that is an absolute approach, or it can be integrated inside the attention mechanism, that is the rotary position embedding method. Position encoding has gone through a clear progression, and each step addresses a real limitation. On screen, you can see the evolution. Around 2017, sinusoidal fixed encoding added to the input. 2018, learned embedding, a lookup table approach, got introduced. 2018 and beyond, relative position methods injecting distance directly into the attention were introduced. And then came the rotary positional encoding. Encoding position through rotation. What stayed the same is the core need. Self-attention is order blind, so position must be injected somehow. Every method solves this same fundamental problem. What change is where the position is injected, what kind of position information is used, and how it scales. Each generation improved on a real limitation of previous one. Okay, let us test whether core concept have labeled. Try to answer each question before I reveal the answer. Sort of pause and ponder. So, question 1. Why is self-attention order blind without positional information? Self-attention compute all pairwise relevance score between token in parallel, using dot products of their representation. There is no sequential processing and no built-in time step. If you shuffle the token, the same set of dot product get computed, and the model has no way to tell the original order from the shuffled one. It treats the input as a set, not a sequence. In one line, what does sinusoidal encoding add to a token embedding? It adds a unique multi-frequency fingerprint vector that tells the model where in the sequence that particular token sits. Fixed, deterministic, computed from sine and cosine waves of different frequencies so that no two positions share the same encoding. What's the intuitive meaning of different frequency across dimension? Fast frequency dimension oscillates rapidly. They are good at distinguishing nearby positions. Slow frequency dimensions oscillate slowly. They captures large scale positions. Together, they give every position a unique encoding, just like a clock with many hands spinning at different speed, produce a unique configuration at every moment. Why might relative position be more useful than an absolute position? Because many language patterns depend on the distance between the token, not their absolute location. The relation between an adjective and its noun is the same whether they appear at position 5 and 6 or position 500 and 501. Relative encoding captures that consistency, which generalizes better across different sequence length and document structure. Let us bring it all together. Self-attention treats input as a bag of token. No inherent order. Positional encoding fixes this by injecting positional information into the token representation. Sinusoidal approach uses sine and cosine waves at different frequency to give each position a unique fingerprint. Fast wave distinguish nearby position. Slow wave captures large scale position. Zero parameter and extended to unseen length. The field evolved from absolute position, which say where am I, to give relative method like rotary position encoding, which says how far apart are we. That shift turned out to be more useful for language understanding and it also generalized better. The original paper showed the learned embedding give nearly identical result to sinusoidal one. The choice became an engineering preference, which later models choosing whatever fits their use case. Now we have everything that transformer needs as its input. Token embedding that carry meaning, positional encoding that carry order. So what happens next? Those combined vectors enter the attention mechanism. And in the next episode, we finally open the engine. What are queries, keys, and value really? Why do we multiply Q by K transpose? Why divide by the square root of D? And how does softmax turns raw score into focus attention weights? We will build the entire mechanism from scratch. If you want to understand that, and so then make sure that you're subscribed. I'll see you in the next one.